Welcome back. We're in chapter 14 on acids and bases, and we are now as far as 14.4 on dissociation constants. If you remember the constant, K sub C, it told us whether or not you have more products or more reactants in a reaction. So we measured the amount of concentration of products after we did an experiment, and we also measured the concentration of reactants. And then through a ratio, we determined whether or not it was favorable towards products or favorable towards reactants. We're going to do the same thing with acids and bases in a very similar way, and I think it's not so hard. It still looks very scary because it looks like math, but it's essentially telling you whether or not an acid is going to completely dissociate in water and be a strong acid, or whether it's going to be a weak acid and leave mostly molecules in water with only a very few ions. So if you have the ions on the right side as if they were products and the molecules on the left side like they were reactants, we could treat this just like an equilibrium constant we did before. So let's get started. A strong acid, remember, is not strong in that it's very potent or it's dangerous, but a strong acid is just called a strong acid because it breaks apart into ions. So if you put a strong acid in water, it will completely dissociate. And we looked at there was a small list of acids that are called strong acids. There's just about 6 of them that you would memorize, and I'll show you the list again. But just know that if you have a strong acid, and we're going to call a generic acid just H because it's going to donate an H, that's a proton, and then A meaning the acid. Okay, so hydrogen chloride, hydrogen bromide, something like this. So the A is going to be some kind of a negative ion. The H is the proton. Put it together, we're going to call that the acid. And then the proton is going to, all of this is going to be put in water, and then the proton is going to attach itself to a water molecule. And if you remember, that's called a hydronium ion. And it's what you consider something to be acidic. You're measuring the amount of hydronium ion in water. And then what's left over is the conjugate base, which is your A minus. It was the anion part of the acid that's left over when the acid gives away its hydrogen. Okay, so a strong acid dissociates or breaks apart into ions into the H plus ion, which then joins with water, and then the negative ion, which becomes its conjugate base. A weak acid doesn't break apart 100%. So a weak acid stays mostly as molecules. So a weak acid, here's what you would put initially into water. This is your proton, this is your negative base. Put it together, you call it an acid, hydrochloric or whatever kind of acid. When you put it in water, a weak acid doesn't break apart all into protons and the conjugate base, but instead mostly stays as the molecule, as the acid. Stays in the water as a molecule with only a relatively small amount of protons that join to make hydronium and then the negative bases, the conjugate base. So a weak acid is weak in that it doesn't completely dissociate in water. It doesn't break apart into water. Um, Citric acid, acetic acid, these acids that are in flavorings are mostly weak acids. So what we're going to see is that a K sub A, and that's what we're going to call it. Remember your constant, we call it as a capital K as your constant. We're not going to call it a K sub C. Instead, we're going to call it a K sub A if it shows up mostly as products, which are your ions broken apart, then you're going to have a very large K sub A. If it's mostly going to show up as reactants, which remember is your molecule, we're going to have a very small K sub A. Okay. We could also have a constant of bases. If you remember, a base is if you put a strong base, it's going to break completely up into water, like potassium hydroxide would break completely into water. So if you were to have a strong base, it dissociates. So it would break apart into ions. So it would be a very large K sub B. And if it stays mostly as molecules, you would have a small case of B. All right. Do you remember if, and I told you this a couple lessons ago, if you have a very strong acid and it gives away its proton to make a hydronium and leaves its whatever's left over, it becomes a weak base. So its conjugate base would be weak. If you have a strong base, its conjugate acid will be weak. So here's an example. A weak acid has an equation written. Okay, so you have the HA, this is an acid, plus water because we're putting it into water. Water is actually acting as a base to receive the proton because the proton is going to join up with the water molecule to make a hydronium ion here, H3O plus. And then this is the conjugate base of the acid. So remember, here is the acid. This is generic. So this is H plus something, H plus chloride or H plus bromide or H plus nitrate, something like that. And then once it's broken apart, this becomes a proton. So it's positive. It joins with the water. It becomes an H3O plus. That's where the plus comes from. This is negative now, and that's the conjugate base. All right, so here on the product side, if you want to think of it as product side, this is now in equilibrium. So if it's in equilibrium, that means every time that one of these hydroniums break apart back again into a proton plus water and joins with the conjugate base again to make the acid, it's happening backwards at the same rate that the acid is breaking apart into a proton plus its conjugate base. That's what these double arrows are indicating. So this is exactly the same kind of a ratio formula that we've done all the way through. We're going to have the concentration of hydronium, the concentration of the conjugate base, divided by the conjugate, or the acid itself, this is a weak acid, times the water. But you have to remember, water here is a liquid. And anything that's solid, pure solid, or pure liquid, we're going to ignore. So I'm going to essentially ignore this water as though it were not there. We're only going to look at this. This is aqueous, this is aqueous, this is aqueous. So it's essentially case of A equals the concentration of hydronium times the concentration of the conjugate base divided by the weak acid itself. And if you have a very large number, then you're going to have a strong acid. And if you have a very small number, a negative exponent of the 1 times 10 to the something, if it's negative, you should say that it's a weak acid. Pretty easy to say. Okay, so let's look at this. Here's some weak acids and bases. Notice that they're all weak because all of these are negative exponents. Once you do them, most of the time, you're going to have this stuck in the water. Okay, hydrofluoric acid is a weak base. It's not one of the 6 that we memorize, so we know it's weak, but it's weak measurable in that when we actually measure the concentrations of it, we get, when you put it in scientific notation, you're going to get a negative exponent for the concentration. And that's showing you that you only have a very, very little amount. You have more reactants. The bottom number is bigger and the top number is smaller. You have a bigger amount of reactants than you do products. And so that's why you end up with something smaller than 1, and that's what's indicated by a negative exponent. And here's bases. It works the same way. When you take ammonia, for instance, NH3, and you pour it in water, most of it's going to be ammonia. A little bit it's going to turn into ammonium plus the nitrogen, but it's a very small amount. It's going to be a negative exponent as well. So you basically write a case of A by taking the hydronium, anything that's aqueous, the concentration of the products divided by the concentration of the reactants, and you're going to ignore pure substances. Anything that's liquid or solid you can ignore, and you end up with something like this. Okay? Hope that helps. I'll see you in class.